Previously, we started talking about or thinking about this example, and we decided to uh, break it into pieces or use partial fraction expansion. And we realized that we are going to have a term with s plus 3 in the denominator, and we are going to have another term with s plus 2, and a third term with s plus 2 squared. Now, we might get any of these terms, or we might not have some of these. For example, B2 might end up being 0, B1 might end up being 0, or A might end up being 0. Okay, let's start with the simple one, A. How do we find A, which is the numerator of s plus 3? Well, s plus 3 is a simple term, so to find the numerator, we just assume we don't have s plus 3. What remains is 1 divided by s plus 2 squared. Substitute in it s equal to -3. So I'm going to have 1 divided by -3 plus 2, which is -1 squared. It's going to be just 1. For B1 and B2, I have to use the formula. Okay, B2, which is the numerator of the term with s plus 2 squared, is going to have, let me go back. I'm substituting K and L in this formula. K is the multiplicity, so the power of my term here. What is the power? K is 2 here, right? So K is 2. What is L? L is what I'm computing here. L is uh, so see the numerator here. L is the counter. L is what goes from 1 to K. So for B2, I would substitute inside. So L is the counter. I'm going to have 1 divided by K minus L. So 2 minus 2 factorial, which is just 0. And we know that 0 factorial is 1. I'm going to have d to the 0 divided by ds to the 0. So what's the 0th derivative of something? It means not take the derivative. Inside the parentheses here, I'm going to have s plus 2 squared f of s, which means just multiply this whole thing with s plus 2 squared. And then substitute -2 for s. So all it means is that substitute -2 in the fraction of 1 divided by s plus 3, which is 1. Now, if the counter goes down 1, so to find B1, when L is 1, I'm going to have 2 minus 1 factorial, d to the 2 minus 1 divided by ds 2 minus 1. So now it's going to be d divided by ds. So now it is actually a derivative, the first derivative of this term. So now I'm going to have the derivative of 1 over s plus 3, which is -1 divided by s plus 3 squared. Substituting -2, I'm going to get -1. So B2 ends up being 1, B1 ends up being -1. Okay, so we talked about Heaviside method. Now, question is, does Heaviside method answer all questions, or are there limitations? The answer is there are limitations. Heaviside method cannot compute the numerator of all fractions. If I have a term like this, remember, previously we talked about terms like s plus 1 squared, not s squared plus 1. If I have a term like this, if I have a term like s squared plus 1, what's going to happen is that I expect to have a fraction with s squared plus 1 in the denominator, which means that in the numerator, I could have bs plus 3 plus c. Why am I going to have bs plus c and not just b? Because now the denominator is a second order or second degree polynomial. So the numerator can have one less degree, which is first degree. So it could be bs plus c. Okay, so Heaviside method cannot find b and c. It is limited. It doesn't have the ability to find b and c here. What it could do is that if you have this case and you know you want to break it into a divided by s plus 2 and bs plus c divided by s squared plus 1, you can find a using Heaviside method, and then you have to multiply both sides by s plus 2, s squared plus 1. So here you get 1, here you get s squared plus 1 times a, and then you find b and c. So look, we found a, then we can take we can solve it by just adding them up and then solving the numerator so that we get on the right hand side what we have on the left hand side, which means c is 0.4 and b is negative 0.2. We have these examples. We can solve them. As you can see, for f1, this is the simpler case. There is no repetition. There's no multiplicity. So pause the video and think about it. What would be the numerator of s plus 2 and what would be the numerator of s plus 3? Well, okay, I hope you tried to solve it yourself. Well, the answer would be the numerator of s plus 2 is to imagine s plus 2 doesn't exist, plug in negative 2 here, which is negative 1, and then here is 1. So the numerator of s plus 2 is just negative 1. The numerator of s plus 3 is 2. Yeah. And other examples which I hope you try to solve them yourself. The second limitation of Heaviside expansion is that if you look at it, if the numerator and the denominator have the same order, then this method doesn't give you the divisor. What? What did I just say? Well, look at this example, f4. If I have s squared plus 6s plus 7 in the numerator, so it's a second degree polynomial, and the denominator is a second degree polynomial too. Let's see what happens. Well, let's break the numerator into s plus 1 plus s plus 2, s plus 3, and therefore let me take the divisor out. So let me take 1 out. What's going to remain is 1 plus s plus 1 divided by s plus 2, s plus 3. What was this term, s plus 1 divided by s plus 2, s plus 3? It was in our examples here, right? That is what we called f1. And we solved it. We realized that if I break f1, I'm going to have negative 1 divided by s plus 2, and then 2 divided by s plus 3, right? So I should have 1 plus what I got before, right? Okay, and that is the correct answer. That is what is correct and what I should get. I should get 1 plus whatever I got before. Now, instead of doing this, which is the correct way of doing it, taking one out and then using partial fraction expansion. Let's mistakenly apply partial fraction expansion or Heaviside method directly to this. As we said here, the previous slide, one of the limitations of Heaviside expansion is that it doesn't give you the divisor. So if I directly apply Heaviside expansion to this, it's not going to give me this divisor. It's going to give me a wrong answer. Let's see. Let's imagine we want to apply Heaviside method to this fraction directly. And let's say, well, I have s plus 2 and s plus 3 in the denominator. So there should be a1 and a2, and I want to find those. If I use the equations, a1 would be -1, and a2 would be 2. So Heaviside expansion tells me that I'm going to have -1 divided by s plus 2, and then 2 divided by s plus 3. So Heaviside expansion claims that this fraction can be broken into -1 divided by s plus 2 and 2 divided by s plus 3. But that is wrong. Why is that wrong? -1 divided by s plus 2, 2 divided by s plus 3. Let me go back. That's what I found for f1. -1 divided by s plus 2 and 2 divided by s plus 3. So Heaviside expansion mistakenly finds for f4 what it found for f1. It cannot capture this divisor here, 1 here. So what should you do if you want to use Heaviside expansion? You have to do this. You have to take this 1 out. You have to do long division. Take the divisor out first. And then when the numerator's degree is smaller than the denominator, then you can apply Heaviside expansion. If you don't remember long division, I have provided 2 links. Look at them. Okay, perform long division on the fraction below. Well, I try to recreate in the numerator what I had in the denominator. So I try to recreate 3s squared plus 5s plus 7. What I'm going to get is 2/3 plus this. Okay, what's the application of partial fraction expansion? We have seen this before. We wanted to use Laplace transform to solve ordinary differential equations, right? You remember we took Laplace transform, we factored everything, we get a fraction, and we didn't know how to take inverse Laplace transform of this. Now that we have studied PFE, partial fraction expansion, we can now break this fraction into pieces, into a term with s, a term with s plus 1, a term with s plus 2, and then a term with s plus 3, and then take inverse Laplace transform. If you want to make sure that the results of partial fraction expansion that you compute with hand is correct, you can use MATLAB. The command in MATLAB for it is residue. So let's do this example. I want to find the numerator, or I want to find the numerators of the terms that come out of partial fraction expansion when I apply it to this equation. So I can break this into s plus 2 and then s plus 3 terms, and the numerator are going to be -1 and 2. Okay, how do I formulate this in MATLAB?